Thank you very much. Thank you everybody for joining this afternoon. My name is Luca Bono, and I'm a technological advisor for battery industry. And this afternoon, battery industry is cooperating with COMSOL to offer you this roundtable of the title From Modeling to Implementation. Simulation in battery design and processes. A fundamental tool to speed up and optimize and make development cost more competitive in the automotive sector. And at the roundtable, first of all, let me introduce the gentleman that is far away from us, is in Sweden, that is Ed Fons. He is the CTO of COMSOL software. And then starting from the other edge, James Hoxey, commercial and responsible for electrification from Williams Advanced Engineering. Francesco Monti, the CEO of Podium Advanced Technologies, Then we have Doug Cross, CTO of Balance Battery, Steve Lambert from McLaren Applied, Head of Electrification, and Daniele Panfiglio, the branch manager of COMSOL in Italy. Welcome to all of you. COMSOL is an international provider of simulation software for the design and research of new products for companies, research laboratories, and universities. COMSOL has a product that is a multi-physics software that enables to simulate a lot of cases. In particular, today we will talk about battery and the behavior of the battery in the electric vehicle, experience and simulation. Okay, welcome to all of you. And I would like to leave the first speech to Ed Fontes to talk about, in more detail, about the multi-physics software simulation. Please, Ed, go ahead.
Yes, thank you. Yeah, so we're talking about batteries today, and the COMSOL approach to battery. We started very early. So I started at COMSOL 22 years ago, and I am an electrochemical engineer. But I was working with electrolysis, and I did my PhD in fuel cells ages ago. But I started working in multiphysics with CFD, heat transfer, and so on. But when it comes to batteries, they are in a way inherently multiphysics because they include material, heat, electric conduction, migration of ions, chemical reactions, electrochemical reactions, phase changes, structural mechanics, and so on. So, and those are usually coupled and non-linear. So that's how COMSOL came into describing batteries, and with the goal of and making a tool for understanding, optimizing, and designing battery and electrochemical systems.
Thank you very much, Ed. James, may I start with you? So, how has the demand of electric vehicle affected the design of the battery after, in this, let's say, this third generation of electric vehicles?
How's that? Right. See, I think as we come into, as you say, the third generation of automotive battery systems, for sure, I think we're starting to see people take more opportunities to reduce complexity. In first and second generations, there was a lot of understanding the new technology, how much risk can you take in the implementation, because the market has to get confidence and adopt the technology. So for sure, we're starting to see more structural packs using the mass of the battery to provide more stability to the vehicle and work the systems a lot harder. So that's one element for certain. And I think on the other hand, we're starting to see consolidation and a lot more modularity. So if you take a look at the VW MEB platform as a great example, we're starting to see a very standardized toolkit which can service multiple vehicles. So on the one hand, there's a lot more performance and almost more specialism. So we're still seeing that innovation. And there's others that have found an acceptable level of performance and they're trying to reduce the complexity and spread that cost across as many vehicles as possible. So it's probably moving in two directions. And I think that will continue for a few more generations yet.
Ah, okay. Really interesting. Steve, at this point, what does importing the efficiency of battery means for automotive industry?
Yeah, thanks, Luca. I think efficiency is going to become more and more important. We've spent a lot of time making sure that battery packs can do the usage of an electric vehicle. They'll do 200-300 miles. We've kind of cracked that now, and there might be batteries that want longer ranges, or vehicles that want longer ranges, but kind of where we are now with the battery pack is probably about right. What we're going to start seeing is a lot more focus on vehicle efficiency. So we see that in the drivetrain, we see that in the motor, in the inverter, but actually I think we're going to start seeing that in the battery. We're going to start seeing lower resistance batteries come in, because actually one way you can reduce the cost of the battery or the whole system is to make it more efficient. So if you can make your battery more efficient, actually you need a slightly smaller battery to go the same distance. And so as we get into the more maturity of EV batteries, into the third wave of batteries, the third generation, efficiency is going to be really important. We're going to start seeing lower resistance batteries, and of course that'll help with fast charging as well. The other thing that'll happen is fast charging batteries will happen. We've got enough power in discharge, but it's charging that's the issue. So getting lower resistances in batteries is going to start to become more and more important in these big battery packs.
Thank you very much, Steve. And let's talk about the two ways, customization or standardization. Which is the path that will drive the automotive market in the future, Doug?
Yeah, thank you, Luca. So I think that's a good question. Customization or standardization, and really it's all about the volumes. So when you look at very high volume vehicles, then you can afford to customize. You can have something which is very bespoke because you're making a lot of them. You can create something brand new for each individual vehicle. You're making 300,000 cars a year, you can have whatever you want. If you want a special size bolt or a special wall thickness on your pack or whatever it is, you can have something which is very custom. But from our perspective at Balanced Batteries, we're looking at more niche vehicles, and there the customers need something which is more of a standardized commodity. So at the module level, we're trying to standardize there so that we can offer a range of modules where the customers can just implement that, and so they can get some level of bespoking. But for them, it ends up being the pack level is bespoke, but the module level is standardized. Does that make sense? Yeah, thank you.
Yeah. Well, just to extend a little bit the question, what is the maximum capacity in standard production that you can achieve now?
Do you mean at the module level or the pack level?
Both.
Yeah, okay. So we offer some really high power modules, and they're well suited for buffer batteries, for fuel cells and that sort of thing. Quite light and around 600 amps, both in charge and in discharge. But in terms of your question of energy, so our modules are good for up to 2.5 kilowatt hours in around about a 10 kilogram module. So that's where we're at.
Thank you very much, Doug. Actually, Francesco, you are running a company that is quite young in this arena, but really ambitious and with a track of success, really interesting in the last 10 years. Which factor have influenced the development of your technology in the battery pack, and what have been the main stages that you have moved through?
Basically, battery means starting from cells and making a final design that enables all the cells giving as much as possible in terms of performances, in terms of life cycle, in terms of overall thermal management. So we all the stages start with the study of emission profile, so what the vehicle should achieve, and then deploy these targets across each single parts of a battery. So if we are talking about optimizing thermal management system, you have to study, and simulation are very important in this part. If you have talking about reducing internal resistance, you have to optimize the electrical connection of all the cells. If you are talking about lightest solution, you have to use different materials or study different mechanical package in order to carry batteries. Everybody knows that batteries are quite heavy, also with respect the vehicle overall weight, and trying to reduce the overall weight is really, really important. So we focus in these different areas, and we focus also in battery management system, because let me say the brain of the battery is the most important thing in order to optimize performances. And coming from motorsport, with motorsport roots, as all the gentlemen here today, is for me really important, because we started doing high performance solution, trying to exploit as much as possible, and we are moving to a much more larger market, mass market, where performance are still important, but overall performances and overall total cost of ownership from the very beginning to the end of the vehicle is very important as well.
Thank you very much. Thank you very much. I know that you have developed your unique technology for the BMS.
Yeah.
Why that choice? Because there are companies offering a BMS.
Yeah, we started developing our own BMS because we would like to control everything in our products in order to exploit the performances as much as possible. And then it becomes a sort of asset, because we are able to implement different algorithms, different strategies with completely different solutions. The last few years we did marine application, we did the railway application, we did eVTOL applications, and having the possibility to control the overall performances of a battery is really a key asset for a company like ours that didn't develop the chemistry, but has to improve the overall package of a battery pack as well.
Thank you very much, Francesco. And talking about BMS and focus on the racing, actually, we have here today Williams Advanced Technologies and McLaren Applied Generation 2 and Generation 3 in Formula E. What can you share with us about the development of those two battery packs, and in particular you also focus on the battery management system and thermal management system?
Shall I start at the beginning? So we developed the Gen 1 solution in 15 months and delivered those batteries to every team on the grid. So it's still a standard part. So if you don't watch the series, it's a standard battery system. And for the first 4 seasons, we were the sole battery system supplier. And for the first 4 seasons, I think you'll sort of understand a bit more about the journey when I pass on to Steve shortly.
James, go ahead.
So for the first 4 seasons, they had to swap cars halfway through the race. So you can only package a certain amount of energy in the standard size enclosure. So there's a lot of evolution that's happened in the last few years, which Steve will come on to in a moment or so, I'm sure. But from a reliability, safety and controls perspective, what was very important to us, especially for the first season in particular, was we had to develop a safety standard. So we had to work with the FIA to create what makes a safe motorsport battery. And in the spirit of motor racing, Nick Heidfeld luckily tested that in one of the first corners of the race. Had quite a large crash. Everything was fine. Survival cell worked. He was fine, and the battery critically was fine. Not an issue. So that's number one, is we had to design a safe battery system, so succeeded in doing that. And from a controls perspective and from collecting data from every race and understanding what the maximum performance could be of the battery, we were able, with the same cells throughout the 4 seasons, to increase the maximum power in qualifying every year. So we were able to improve confidence in that 15-month design to delivery, and increase the sort of spectacle of the qualifying event every season with the same technology. So I think for us, we learned a lot about reliability, moving those sort of development opportunities through each season. So every season was a slightly iterated design, and finally sort of got to the end of season 4 and Gen 2 started.
Yeah, so McLaren applied, did the Gen 2 battery pack. I think what's interesting when you look at Formula E is the relationship with automotive technology, particularly on the batteries.
This interruption was sponsored by Battery Tech Europe.
Sorry, thank you for waiting. I think the relationship between automotive technology and the motorsport in Formula E is really interesting, particularly when you look at the battery. In the Gen 1 battery, it was developed in a very sort of motorsporty way, I'm assuming, but because there weren't electric vehicle batteries out there on the market at that point. It was before a lot of the EVs had come to market, so it was developed in quite a prototypey way, I think is probably fair to say. The Gen 2 battery was different in some ways, because we actually then said, okay, a lot of investment has happened in automotive, and we want to take advantage of that. So we had very, very standard automotive cells. The way they were put together was relatively standard. The BMS was very automotive. We did that because where Formula E was, it needed reliability, it needed to establish itself then as a long-term series. We did push the boundaries in some areas, particularly things like using the battery as a structural member. Part of the battery was stressed, and so that became part of the floor of the vehicle and the structural member of the vehicle. And then I think what's really interesting is when you look at Gen 3, and I'm sure James will talk about that in a second, but Formula E have said, how do we keep the technology in the series relevant? And so they've looked at where automotive is going and have said, actually, let's get ahead of where automotive is, and let's look at fast charging. Let's see what we can do, because that's where the future of automotive will be, is in fast charging. And so there's a bit in the public domain about it, but the part of the Gen 3 battery will be all about fast charging. So that's really Formula E saying, okay, we want to get ahead of automotive and use it as an opportunity to develop the new technology that will then trickle down into automotive. And I think that's really important. That's a great place for motorsport series for Formula E to be, and it's something Formula 1 has done for many, many years, and something Formula E needs to do as well. And it's a good thing.
Okay.
Yeah. So do you want me to pick up on Gen 3?
You are in 2 companies actually that are at the top of the engineering technology in this field. So what are the opportunity and which technology we can see in the future And James, if you can spend some word more about your experience with Gen 3, and Steve, you are today more focused on the electrification, high power electrification. If you can spend a little more about your technology and what is the future of new application in terms of flying cars, or let's say the eVTOLs.
Okay, so I think we finishing with Gen 3. Steve's absolutely right. So we are looking at fast charge. So to deliver a representative fast charge event in a race, the sort of automotive packs of today wouldn't be able to sort of manage the power requirements that we're going to have to move in a short pit stop to represent a meaningful charge event. We're talking about seconds in a race. So we're having to think about, I suppose, introducing two things. One is a high amount of power in fast charge. So I think the Porsche Taycan has the highest fast charge in the market, about 350 kilowatts. So we're going above that by nearly an order of magnitude. And that will enable some exciting demonstration. It will allow strategy to develop a little bit more in Formula E as well. So I think that the platform that the Gen 2 battery has delivered is that sort of consistency, the reliability in the racing has continued. And now the Formula is in a place where it can take a few more technical risks to make it more of a spectacle. So it's exciting to see a bit more strategy being introduced to the race. Where will people take that charging event? How are they going to simulate the best time to do it? So I think it will maybe have a few more echelons of Formula One type thinking. We're starting to see that be introduced. So I think that's really positive. I think I'll sort of let Steve lead the charge with where else are things going, and I'm happy to jump in afterwards with a few examples of where we are as well.
Yeah, so thanks, James. Yeah, so we see and I mentioned it earlier, we see efficiency as being really, really key. Mentioned about efficiency in the battery. At McLaren Applied, we could say that the battery has been the low-hanging fruit for a number of years, and a lot of development has happened on that. But we're looking at the wider drivetrain now. We're in kind of the second wave of electrification at the moment, where all of the OEMs are trying to bring vehicles to market. You can't go into a dealership now without seeing an electric vehicle. And so all these vehicles are coming to market, and at the moment there's more demand than supply. But as soon as supply starts catching up with demand, they're going to be competing with each other. And the way they'll compete is through efficiency, because the more efficient you are, the faster you'll go on the further you'll go on a charge, the quicker it will be to charge, the lighter the vehicle will be, the more responsive it'll be. Everything will get better with efficiency. So we're looking now at not just the battery but the drivetrain. So making sure that we're using silicon carbide inverters, which are higher efficiency, to optimize the whole vehicle architecture. Because when you start looking at the whole vehicle and optimizing for efficiency, you get a virtuous cycle. So you get a little bit more efficient, you generate less heat, you need less cooling, it gets a little bit lighter, you can make your systems a bit smaller, you need less energy, therefore you get a bit more efficient as a vehicle, and you start going round in a circle, making it more efficient and a better vehicle. So that's where we expect the third wave to be, is all around efficiency, and that's really what we're focusing on. The other trend that we're seeing is drivability. So at the moment, electric vehicles are great fun to drive, but they're a little bit one-dimensional. You put your foot down, you accelerate, your head goes back, but that's about it. They don't necessarily go around corners very well. They're not very responsive. It's all about acceleration. One of the things we're finding, I should say, with our inverter technology is because its background of development has come from Formula One and Formula E. That dynamic response is built in. We've spent many years developing the throttle response of an engine. We haven't done the same yet for electric vehicles. However, what we found is, particularly in Formula E, there's only a couple of things that differentiate the vehicles. The vehicles are the same, apart from the drivetrain and the driver. So ignore the driver. He's a soft, squidgy thing that sits behind the wheel and looks good. Actually, the drivetrain is the thing that makes it. And if you get it more efficient and more responsive, that's what will win you races. And ultimately, that's the technology that will come into automotive in the future and make vehicles more competitive, more engaging, and you more likely to buy them. So that's what we see is coming next, really.
Thank you very much, both of you. Doug, actually, Steve was talking about efficiency, drivability, and that is connected with the architecture of the vehicle. Do we have to expect more integration of the battery in the car body, or we will see more structural batteries?
Yeah, so I think it was interesting to hear Steve talk about the structural nature of the Formula E battery pack. And we see there is a tendency to try and reduce weight and try and reduce cost in battery packs at the moment. And to do that, people are trying to reduce the number of components and yet make them more integrated into the vehicle. So some of the things we've been seeing are people are making, I guess you might call them topless battery packs, where you've got the battery as an enclosure, but there's no top to it, and they're bolting that up underneath the vehicle, and the vehicle structure itself becomes part of the battery pack. So it's much more integrated, and you're removing a load of weight when you do that. That's one thing that we've seen. We've also seen other customers who are doing a similar thing by bringing the battery pack in from the front end. And one of the things, if you look at a lot of the advertising around battery cars, you see that the pack itself is often it's mounted under the floor, and you'll see people who are advertising vehicle skateboards. And if you think back to the history of the car, a long time ago, we were making vehicles based on ladder frame chassis. And there's a reason that we moved away from ladder frame chassis to a more unibody. And it's about structural integrity of the vehicle and about handling dynamics. And so we're anticipating, and we're not starting to see it yet, but we are anticipating that you're going to start seeing much more of that complete vehicle architecture where the batteries are built into the vehicle rather than as a separate pack which is underfloor and then just added on later on.
Thank you very much, Doug. Very interesting. Ed, at this point, how the simulation software can support the design of future cars and batteries, as well as the thermal management system that will get more and more important in this case.
Yes, so as I said before, so the phenomena that occur inside a battery are non-linear and coupled, and there are many of them. So the first step where we can support is to understand, of course, and that understanding hopefully leads to new ideas, and those new ideas can then optimize and also control. So, but if we look at today's battery industry and users of batteries, there's such a large expansion. So there are not a lot of engineers, there are not enough engineers that understand the batteries. So in that sense, it's important for us, software manufacturers or software developers, to make the software easy to use so that the domain experts have the advantages of using high fidelity multi-physics modeling to not only optimize but also characterize the batteries to see what's happening inside the battery as a result, by comparing the measurements, by doing parameter estimations, by monitoring the battery system. And that has to be doable for somebody that doesn't have 10 years of experience in electrochemical engineering and batteries.
Thank you very much, Ed. And James. Okay, sorry, Daniele, please.
I just want to add, since I visited some booths during these days, that an electric car is not only a battery pack or thermal management, but there are a lot of other devices that has to be improved. For example, electric motors, transformers, and so on and so on. So simulation can help. I mean, in all of different design departments. So that's why, I mean, a software is not vertical. I mean, only for the battery pack or the battery design. That's
Yes,
an experience from here.
Thank you very much.
That's a good point. That's
Really,
system
really.
integration too. That's also complex, and modeling helps in that, of course. System integration. So
Yeah, correct. Thank you very much. Actually, James, talking about simulation, how simulation can support also the innovation of the systems?
Yeah, I think it's increasingly playing a critical part in the adoption of battery technology into electric vehicles. I sort of presented briefly yesterday a slide looking at how we correlate our battery design through a virtual analysis into a physical test. We can't get away from it. There will always be a physical test at the end of any development program. You have to test hardware. However, it enables us through simulation to sort of look at several scenarios. I think we've talked about these different battery system structures that are coming into production in some instances, or plan to go into production, and we need to test various sort of hypotheses. And to do that with physical hardware would take too long, would be too expensive, and actually it'd just be very risky in some scenarios. So for those three reasons alone, simulation is becoming more and more significant for us. Again, when you start talking about cell to pack methodology, using larger cells, thinking about propagation, thinking about different chemistries, I mean, you can model nearly all of this. So if you have a very good model, you can have a relatively good answer to a hypothesis in a relatively short amount of time. So it's a massive part of what we do. It's how you stay at the front of any technology for us.
Thank you very much, James, really. Francesco, at this point, actually, clearly it's important to predict the behavior of a battery, in particular in competition. And what do you have learned from racing? And from that, how can you move your experience to the street cars?
Yeah, from racing, you for sure have lots of chance to learn a lot in terms of behavior, in terms of extreme condition of managing the battery and all the chemistry behind it. But moving from a racing application towards a railway application or a street legal application is really important, because when you develop a battery for a 24-hour race, you know exactly which is the emission profile. You can predict, you can simulate, you can also test the battery in that exact condition. Talking about a street legal car or other application, emission profiles may vary a lot. Environmental conditions are really difficult or more complex to predict, and simulation and algorithm becomes more important with respect to a racing application. So what we experience and what I can say is that street legal or other applications are much more complex and much more difficult in terms of engineering effort with respect to motorsport projects.
Thank you, Francesco. Can you share a little bit about your experience on Formula One cars, Steve?
Yeah, thank you. So, so we, I can't say who, but we've been involved in the KER system in Formula One, including the battery. And simulation plays a really important role in that. But what's really interesting, when you compare Formula One and Formula E, the role of the simulation is very different. In Formula E, we have to use the simulation to understand what's going on with the batteries. Because it's a standard battery that every team uses, there can't be an advantage for any team. We have to have completely the same power available, the same current, the same energy. It has to be completely standardized across the entire paddock. So we have to use simulation to make sure that everything is exactly the same. So what we're not looking for is any variations. We want everything to be the same so that we can ensure the same state of health, the same power across that entire grid. In Formula One, it's a little bit different, and you're looking for any small piece of benefit you can get out. So you may build a number of batteries, and then there'll be one or two of those that are probably performing a little bit better. That maybe they might have a slightly smaller internal resistance, they may get less hot, whatever that might be. And so you're looking for those little benefits or ways you can run the batteries to get those little benefits. And so there's a big difference then between that sort of single bespoke designed battery in Formula One, where you're trying to get the absolute last little pinnacle 0.1% out of it, and something like Formula E, where you've got to make sure everybody is exactly the same, and actually you reduce the performance to make sure you get there to some extent. Still within limits, but you want to make sure that nobody has any performance benefit. So there's some really interesting differences in how you use the data to do that. And of course, the more data you have, the more likely you are to spot those differences, whether you want those differences or you don't want those differences.
Thank you very much, Steve, for sharing. And Ed and Daniele, actually, is it possible to predict the end of life of a battery pack and aging phenomena with simulation?
Yeah, so you can definitely predict the risks depending on the history of the battery. For example, we mentioned that in our pre-discussions, like effects like plating when you're fast charging. And also by correlating your measurements, your data to the model, you can also predict where the battery is heading. But of course, and maybe also for a large group of batteries that are operating a certain way, you can also make predictions. But in our pre-discussions to this meeting, I remember that we mentioned, I think Steve mentioned the digital twins. So that's a way to make predictions using the models. And so like Francesco said, I think he called it strict legal. That's the term you use. That they operate at so many different conditions, and that is more difficult than the Formula E racing applications. So in that sense, the models, through the use of digital twins, through the use of the fact that you can always correlate and go back, and then also use the knowledge that you have from exactly like James said, that the model gives you a very clean cut from hypothesis to results. So if you think that the result should be this, you run the model, and it's not like that. You haven't understood. So in that sense, the model, together with the measurements and a device like the digital twin, will help you predict the life, the end of life, and the status of the battery. That's what I think.
No. Okay.
Daniele, would you like to add something?
No, maybe we can mention also about the importance of the material data. So if a simulation tool is a tool, so it's a sort of advanced tool for the designers. But if you input some wrong data, you will fail your simulation. So it's anyway important to understand that the efficiency of a simulation is given also from the interaction by the end user with the software. We can implement the best solution as possible, but if we give in the wrong hands, I guess we can fail with the simulation, and also with an experienced product or an electric car or something like this. So.
But yeah, and similar, there are uncertainties. So if you take a single battery cell, there's a deviation, a natural deviation in the material properties and in other properties. So there's an uncertainty, and so that's the importance of characterizing the battery as you go.
Thank you, Ed, for this clarification. James, what do we have to expect for the future in case of innovation and improvement needs in the battery pack?
So I think from our perspective, thinking about control systems in particular, what Daniele and Ed say is right. Having the toolkit is one element. It's actually the so what factor. So how do you use that information? How do you create value from that information for your partners? So a lot of the innovations that we see being accelerated are how you sort of improve your battery management system to provide more data to the end user. We're in an interesting position at the moment whereby through our acquisition by Fortescue Metals Group or Fortescue Future Industries, we're now leading the decarbonisation of a whole mining fleet. And the business case for that is very simple. It's about how cheaply can you run that fleet per hour. So for us, we need to get as much data as we can out of one of the most expensive components in the vehicles, being the battery system, to understand the optimum point to take that battery out for a refresh if it's getting near to the end of life, to spot a potential latent fault in the battery pack and rectify that at the first opportunity. So we can see, on the one hand, for commercial fleets, having these sort of digital twins and being able to predict an outcome will be massively valuable. We see it already with things like GM's OnStar service, similar approach. And I think we see a lot more of that coming. I think from the other side, the mechanical side, in terms of innovation, I think it's relatively well known at this point that there's a massive misalignment between sort of where the vehicle industry wants to go for electrification in terms of cells. What's kind of coming out of the ground is on a much flatter line at the moment. And so therefore, looking at new chemistries in applications that maybe weren't foreseen previously. So we're currently working with one large OEM who's looking at cell to pack, not from a reduction of complexity perspective, but actually, if we go cell to pack, can we move from NMC to LFP and still have a 300-mile vehicle because of the volumetric efficiency? So I think we're starting to see some leveling of a 300-mile car is okay for us. How do we do that cheaply, and how do we secure the supply chain? So I think a lot of the innovations aren't necessarily coming from a kind of classic motorsport sexy application space. It's coming from we have to secure and supply things for our customers. It's a really fascinating switch. People are planning, less than $100 a kilowatt hour. They're not just going to get it by knocking down the cell costs. That's not going to move. So there's plenty of opportunities.
Yeah, interesting point of view. Yeah. Francesco, so clearly BMS algorithms are playing an important role in the optimization of a battery pack. Can you spend some more word talking about the state of health, state of power, in both cases, racing as well, street importance to maximize the efficiency of the battery pack? And Steve, what about the state of functionality, in particular during the discharging of the battery pack?
Yeah, BMS is devoted to taking care of the overall performances of a battery, and state of charge, state of health, state of power means giving the vehicle, the end user, the necessary information to exploit as much as possible in a safe way the battery pack, ensuring also the life cycles, because the cost of a battery pack is still a very huge part of the cost of the overall vehicle, and ensuring that you can use in a good way to ensure the life cycle is really important. And the information of state of health is really important also for